Hello everyone, in this video we'll be picking up where we left off in section 9.8. So we're looking at example C here and we're trying to find its radius of convergence. So first let's go ahead and say where this power series is centered at. And since it's just x by itself and not x minus c or x plus c, we know that this is centered at x equals to 0. So for the x value, x equals to 0, we know that this converges. In order to find where else this converges, we use the ratio test. Right? So for x not equal to 0, let's let u sub n be equal to our terms. Right? So negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And then we perform the ratio test on u sub n. The limit as n goes to infinity of u sub n plus 1 over u sub n is equal to the limit as n goes to infinity. And here this is u sub n is a fraction, so I'm going to write u sub n plus 1 and then multiply by the reciprocal of u sub n. So u sub n plus 1 would look like negative 1 to the n plus 1, x to the 2, then we're plugging in n plus 1 for n, over 2 n plus 1 for n. And then now instead of dividing by u sub n, I'm going to multiply by the reciprocal. So flip it upside down. So I get 2n plus 1 factorial over top of negative 1 to the n, x to the 2n plus 1. Okay, so a couple things are going to happen. Let's look here. When I multiply this out, I get 2n plus 2 plus 1. In other words, I get 2n plus 3. And same thing's going to happen here. 2n plus 2 plus 1, which is 2n plus 3. Okay. Also, since I have absolute values, this negative 1 to the n or n plus 1 is going to be not important to us. So I look at the limit as n goes to infinity of x to the 2n plus 3. And then we'll leave the 2n plus 1 factorial alone, and then I end up with x to the 2n plus 1 and 2n plus 3 factorial here. Okay, so now we need to realize something, or a couple of things, right? 2n plus 3 factorial, I can rewrite this as 2n plus 1 factorial times 2n plus 2 times 2n plus 3, right? Because 2n plus 1 is every number being multiplied before 2n plus 1 multiplied up, then multiplied by that n plus 2, then multiply it by 2n plus 3, and I get 2n plus 3 factorial, right? So that's an important thing to realize. The other important thing to realize here is that this is 2n plus 3 up here. This guy right here, I can rewrite as x to the 2n plus 1. Why am I choosing to split it up like that? Well, because I know I want to cancel at that x to the 2n plus 1 there, and then I can multiply it by x squared, right? Because then when I add it up, I get x to the 2n plus 1 plus 2, and I'm back to x to the 2n plus 3, right? So now I rewrite this as the limit as n goes to infinity of x to the 2n plus 1 times x squared times 2n plus 1 factorial over top of x to the 2n plus 1 times 2n plus 1 factorial times x to times 2n plus 2 times 2n plus 3. And now some things are going to cancel out, right? X to the 2n plus 1 cancels out, 2n factorial cancels out, and I'm left with the limit as n goes to infinity of x squared over top of 2n plus 2 times 2n plus 3 and the absolute value. Okay, so just as before, this x squared is independent, so I can pull it out front. So this looks like x, the absolute value of x squared. But the absolute value of x squared is redundant because x squared is always positive, All right, so then I multiply it times the limit as n goes to infinity of 1 over 2n plus 2 times 2n plus 1. I'm sorry, 2n plus 3. And again, I can forget the absolute value because n is always positive because it's the indices here. So I get this. And now I get x squared. What is this limit? This limit is 0. So in other words, I get 0. Right? Remember what we were doing. We're looking at the ratio test. Right? 0 is less than 1, regardless of what I plug in for x. Right? So in this case, by the ratio test, what ends up happening? The series converges no matter what I plug in for x, right? Because no matter what I plug in for x, this is still going to be 0, which is less than 1, which means that it's going to converge, right? So by the ratio test, this converges for all x that's not equal to 2, and we know that, or I'm sorry, 0. So in other words, it's going to converge for all x. Because we know that it converges for all x not equal to 0, because that's what we did. We know it converges at x equal to 0 because it's centered there. So this converges for all x. Right? So what does that mean? If it converges for all x, the radius of convergence is r equals to infinity. Right? So what does this look like in our graph here? We know at 0 we're good, right? And we also know that for every other value we're good. So the interval is just the whole number line, right? So what does example C and example A tell you? Well, in both example C and example A, I know that the x kind of vanishes, right? And so if I end up getting 0 here as my limit, which multiplied times whatever x is fine, and it still equals to 0, then I know that's the case where I have r equals to infinity. If I ever end up getting infinity for my ratio test, I know that regardless of what x I plug in, it's infinity, so it's greater than 0, so I know that my radius of convergence is infinity, right? Or I'm sorry, is 0, right? My radius of convergence is 0 in that case. So these are kind of, A and C are kind of our special cases. Most of the time, we're going to get a radius of convergence like example B there. So let's look at one more here. This is, we'll look, first let's figure out where I'm centered at, right? So here I have x plus 1. Well, remember, I'm centered at x minus c means I'm centered at c, right? So what's the value that I'm subtracting from x? The value that I'm subtracting from x is negative 1. So this guy is centered at x equals to negative 1. Okay. So now for x not equal to negative 1, again, we let u sub n be our terms that we're adding up. So negative 1 to the n, x plus 1 to the n, over top of 2 to the n. And then we perform the ratio test, right? The limit as n goes to infinity of u sub n plus 1 over u sub n equals to the limit as n goes to infinity u sub n plus 1, so we get negative 1 to the n plus 1, x plus 1 to the n plus 1, 2 to the n plus 1, and now we multiply by the reciprocal, so I get 2 to the n over top of negative 1 to the n, x plus 1 to the n. So in this example, since we've done a few of these examples, let's go ahead and try to cancel some stuff out without rewriting, so we practice that. So the absolute values, again, the negative 1s cancel out. I have x to the n plus, I have x plus 1 to the n plus 1 power. So remember, that's really x plus 1 to the n power times x plus 1 to the first power. and I have x plus 1 to the nth power here, so this whole guy is going to basically cancel out with the x plus 1 to the nth power. So that's how I like to rewrite it, so that way I realize that all I'm left with is the plus 1 part. And same here, this 2 to the n plus 1 is really 2 to the n times 2, and now I get 2 to the n will cancel out with the 2 to the n, and then I'm left with the plus 2. Or I'm sorry, I'm left with the 2 to the first power. So here I get the limit as n goes to infinity of x plus 1 over 2. Right? So if that confused you, what I just did, go ahead and do the rewriting of everything and cancel them out. But if you're able to follow what I just did, you can save yourself a little bit of time. This is a limit with n. This has no n's in it, so it's just a constant. So I know that this is just equal to x plus 1 over 2 and the absolute value. Okay, so what do we know? We said this is the ratio test, so if this guy, so by the ratio test, the power series converges if whatever our limit was, which in this case it was x plus 1 over 2, is less than 1. Right? So let's scooch that over a little bit. We'll put it all in one line. Okay, but I can do some more work. X plus 1 over 2 less than 1. Remember, we want whatever is here inside the absolute value to just be x minus the center. Right? Right now we have that divided by 2, so we got to be more careful. By rules of absolute value, I know this is x plus 1 over top of the absolute value of 2. Right? But what's the absolute value of 2? The absolute value of 2 is 2. Multiply by 2. So I get x plus 1 in the absolute value is less than 2. So now I have my x minus c is less than this value, and so this value means that our radius of convergence is r equals to 2. Right? So in this case, where were we centered at? We were centered at -1. So 2 bigger than that would be +1, 2 smaller than that would be -3. And I know that I'm good at 1, and I'm good for these values in between where my radius is 2. Right? Okay, so now let's look at differentiation and integration of power series. Okay, so a power series, remember, is just infinite powers of x being added up. So that's what we're going to look at when we look at differentiation and integration, right? If we just have powers of x, we're able to take the derivative of that just by the power rule, and we're able to take the antiderivative of that just by the power rule. So if this function f of x, which equals to this power series centered at x equals to c, looks like that, which is exactly our power series, and it has a radius convergence of of r greater than 0, right? So in the case where it's not just a radius of convergence at one point, then on this interval from c minus r and c plus r, so in other words, on the radius of convergence, right? So this is c plus r, c minus r, c plus r. Then on that interval, we know that it's differentiable. And so this is how we find the antiderivative and the derivative. So in order to find the derivative of it, what do? Well, we just do the power rule, right? If x is my variable right here, then I take n goes down to the front, right? Because if I were taking like x to the x cubed, I would do 3x squared, right? Power comes down, bump the power down by 1. So that's what we do. The power comes down, and I bump the power down by 1. So I'm just doing the power rule here on each term. So I get exactly this, right? A sub 0 goes away because it's a constant, and then I get a sub 1 x. So here I get a sub 1 x, so it just becomes a sub 1, and then plus 2 a sub 2 plus 3a sub 3, because again, I'm doing the chain rule for each one of these parts. And then if I take the antiderivative, again, the idea is the same, right? Here's my x, so what do? I bump up this power by 1 to n plus 1, and I divide by the new power, right? That's exactly what this rule is. And then, of course, I have to have my plus c because I'm taking the antiderivative. So essentially what this is saying is that if I want to differentiate or take the antiderivative of a power series, then I just do it term by term. Right? So sometimes it'll be easy to do it, like with these, it's really easy to just look at it and do it by the formula here, and sometimes it'll be easier to look at it term by term and do it term by term and then rewrite the formula. So you'll see what I mean when we do these examples. So the radius of convergence of the series obtained by differentiating or integrating is the same as that of the original series. So the radius of convergence is the same, whether I differentiate it or integrate it. However, the interval of convergence can change a little bit because of the endpoints. Remember, so that I said that we're focusing on when it has open intervals. We're not really paying attention to when the interval is closed or not. So that really doesn't affect us too much, other than just kind of a point to note. But the radius convergence stays the same. However, the endpoints can change a little bit. Okay, so the first question says, so example 3 here says, consider this function, which looks like the series from n equals 1 to infinity of x to the n over top of n factorial, and that looks like the terms x plus x squared over 2 plus x cubed over 3. Notice that this series starts at n equals to 1. Why? Well, because if I had n equals to 0, then I would be dividing by n, which wouldn't work. Right, so this is one of those cases where I have a series that starts at n equals to 1, but that's not going to affect anything we do here for finding the radius of convergence. Okay, so we want to find the radius of convergence for each one of these. So the first one I don't have to do anything, right? I just know what f of x is. It is x to the n over n factorial, or I'm sorry, over n. So where is it centered? X equals to 0, right? And then in order to find the radius of convergence, we do the ratio test. So if x does not equal to 0, then what do? We let u sub n equals to x to the n over n, and then we do the ratio test, right? The limit as n goes to infinity of x to the n, or u sub n plus 1 over u sub n. So I get x to the n plus 1 over n plus 1 multiplied by the reciprocal, so I get n over x to the n. So the limit as n goes to infinity of x to the n cancels out with x to the n, and I'm left with n times x over n plus 1. So again, that x is a constant, so I can pull it out front. I got to keep the absolute values around it though, so I get the absolute value of x times the limit as n goes to infinity of n over n plus 1. Hopefully by now we're able to look at this and see that this limit equals to, not 0, equals to 1, right? Because if I would divide by n on every term, I'd end up getting 1, and so I end up getting just the absolute value of x, right? So what does that mean by the ratio test? The power series converges if the absolute value of x is less than 1, right? Whatever my limit was, which is the absolute value of x, is less than 1. So what does that mean? That means my radius of convergence is r equals to 1, right? And the claim is the radius of convergence is going to stay the same whether I integrate or take the derivative. So in each one of these cases, I should be getting that the radius is equal to 1, right? But let's go, that's the point of this problem, is to figure out, show that, right? So in order to find the radius of convergence for the integral of f of x dx, I first need to integrate it, right? And so that's what we're going to do first, right? So the integral of f of x dx looks like the integral of f of x is the sum n equals 1 x to the n over n over n dx, right? And so since this is our first time doing it, we'll go ahead and do it term by term, and then I'll show you how you can kind of jump, right? So we want to find the integral of this whole series. So let's write out what the series is, right? For n equals to 1, we get x over 1, so just x, right? Plus x squared over 2 plus x cubed over 3 and so on, and we want to integrate that. Right, and here's the series up here. So if we're going to integrate that, we do that term by term, right? So the first term would be x squared over 2. The second term, normally we would multiply, I'd see that this is x cubed over 6, but let's go ahead and leave it as x cubed over 2 times, over 3 times 2, right? 3 being the new power and 2 being what's left over. I'm just doing that so that way we can see the pattern here to write a formula for the summation, right? And then I get x to the 4th over 4 plus times 3 plus so on. And then what happens at the very end, we can't forget our plus c, right? So now that we have our antiderivative, because we did this term by term, that's what the theorem up here told us, is that we could differentiate or we can integrate term by term, we need to write a formula, right? So this is for n equals to 1 because we start at n equals to 1. This is n equals to 2, n equals to 3. And so let's write a formula for what is happening here. So for n equals to 1, I know that I need x squared. So in other words, I need to bump up the power by 1. Right? If n equals to 2, I know I need x cubed. If n equals to 3, I need x4. So I know I always need to bump up the power by 1. And then what do? Well, I can't really see in the first term what's happening with the denominator, but if I look in the second term, right, I get the new power, which is n plus 1, and I multiply it by the old denominator, which was n, right? So the 2 is the n, and the n plus 1 is the 3, and then plus c, right? So this is my antiderivative. Now, if you're able to jump from here to here, that's perfectly fine, right? Because if I look here, this is just integrating term by term, so each term I'm going to bump up the power by 1 and divide by the new power, right? And so my new power would be n plus 1 would be multiplied there, right? So if you're able to see this, that if I were going to take the antiderivative of this, I would get x to the n plus 1, and then I divide by my new power, and that gives me my formula, then by all means. If you're not able to see that, then write out each term, take the antiderivative of each term, and then find the formula, right? Either are perfectly fine. So now we've got our integral, and so now we need to look at the radius of, we need to find the radius of convergence, right? So again, for x not equal to 1, because not equal to 0, because we know this is centered at 0, we let u sub n be equal to x to the n plus 1 over n plus 1 times n. The c is not going to affect what our radius of convergence is because it's just a constant. And then we do our ratio test as the limit as n goes to infinity of u sub n plus 1 over u sub n. So here, when I plug in n plus 1 here, I get n plus 1 or n plus 2, right? So I get x to the n plus 2 over n plus 2, n plus 1. And then when I multiply by the reciprocal, I end up getting n plus 1, n over x to the n plus 1. Well, remember that x to the n plus 1 is really, x to the n plus 2 is really x to the n plus 1 times x, right? So that way I'm able to cancel here. I get x to the n plus 1 cancels, n plus 1 cancels, and I'm left with the limit as n goes to infinity of x times n over n plus 2. So again, I can factor out the absolute value of x because it's a constant. The limit as n goes to infinity of n over n plus 2. Again, this limit is equal to 0. right? Practicing with limits, you can either think about this as a horizontal asymptote or divide by the highest power of n in this case, but either way, or not 0, sorry, 1. I get 1 there, so this is just the absolute value of x. So as always, by the ratio test, the power series, which in this case was the integral of f of x dx, converges if whatever my limit is, which was the absolute value of x, is less than 1. So what does that mean? Just as we expected, my radius of convergence is the exact same as is 1, which is the exact same as the original function. Okay, so now I look at the derivative, right? So again, f of x is equal to n equals 1 of x to the n over n. So when I go to take the derivative, f prime of x, well, actually, let's write out what these terms are. So I get x plus x squared over 2 plus x cubed over 3, and so on. So if I do this term by term, the derivative of the first term is 1, plus the derivative of the second term, well, the 2 comes down out front, and then it cancels out with the 2, so I'm just left with x, plus the 3 comes down out front, it cancels out the 3, so I'm left with x squared, plus, and so on, right? So what does that series look like? This one's not too bad to write. So I start at n equals to 1, and it's just going to be x to the, well, if n equals to 1, right, careful, this is n equals to 1, n equals to 2, n equals to 3. It's tempting to just write x to the n, but that's not good enough, because then we would start out with x, and that's not what we start out with. We start out with 0, so I need n minus 1. Right? And now if you notice, if you look here and take the derivative, what do we do when we take the derivative? We bring the power down out front, so the n and the n would cancel out when I bring it down out front, and then I bump the power down by 1, which is x to the n minus 1. Right? So maybe you're able to jump from here to here, maybe you're not, but we've done that. Right? So once again, we're going to find the radius of convergence, show that it's still 1 in this case. So if x is not equal to 0, right, because our center is at 0 in all of these, because I'm just left with x by itself, then we let u sub n be equal to x to the n minus 1. Then what do we get? We do the ratio test. Limit as n goes to infinity of u sub n plus 1 over u sub n. Limit as n goes to infinity of, if I plug in n plus 1 here, I end up getting n plus 1 minus 1, so in other words, just n, right? So I get x to the n over x to the n minus 1, because n minus 1 is u sub n, right? So here we'll go ahead and write out what the algebra is. So x to the n I have to leave alone, but x to the n minus 1 I could rewrite as x to the n times x to the minus 1, right? Because if I multiplied those two guys, then I would add their powers, which I'd get n minus 1. So x to the n's cancel out, so I get the limit as n goes to infinity of 1 over x to the negative 1. So x to the negative 1 in the denominator, remember, if it's a negative exponent, we can always bring it to the numerator and make it positive, right? So I get the limit as n goes to infinity of just plain old x. And then the limit has to do with n's. X is a constant, so I just get the absolute value of x. So what do you know once again? By the ratio test, the power series, which looks like f prime of x, the derivative converges for whatever this limit was, is less than 1. So for the absolute value of x is less than 1. And what does that mean? That means my radius of convergence is r equals to 1, right? So in this example with a, b, and c, we practiced taking the antiderivatives and the derivatives, and we showed that regardless if we take the antiderivatives or derivatives, we end up with the same radius of convergence of our original function. So that's all I have for 9.8. Thank you.